Hi, everybody. My name is Amos Grop. I'm from Desi AI, and my talk is about how to maximize your CPU compute power for CNN inference. So again, I'm Amos. I'm a research engineer at Desi AI. I'm part of the Neural Architecture Search Research Group led by Professor Ran Elianiv. Prior to that, I did my master's at Weizmann Institute of Science in the field of geometric deep learning, and glad to have all of you here today with me. What we're going to talk about in the next 30 minutes or so is about model efficiency and how to boost deep learning model performance on a CPU. We'll discuss how to improve runtime performance generally using various techniques in order to improve the performance. We'll share with you recent results of our NAS-based solutions. To wrap it all up, we will share some best practices for further maximizing CPU inference from the engineering perspective. Okay, so let's start. So since 2014, deep learning models are getting more accurate, but at the same time, they getting bigger and slower and more compute hunger. And for instance, in this graph, we see the evolution of Imagenet classification models since 2014. So we start on the bottom left corner with AlexNet. And what we see on the y-axis is the top one, Imagenet accuracy, and the x-axis is operation in gigaflops, and the size of the circle is the number of parameters. And as you can see, we do get better accuracy, but at the same time, we get bigger, larger, slower models. And this is just the tip of the iceberg, because in OpenAI famous GPT-3, which is a very famous language model, we have 175 billion parameters in this model. You can't even see this circle. It will fill all of this graph. And they claim that GPT-4 will have 500 times more parameters than GPT-3. And one can only guess what will be GPT-17 in the future. But at least a gazillion parameters. But as deep learning practitioner, our goal is not only to find accurate model, but also we want to find research efficient model which can perform well in production. So in this talk, we'll examine different aspects that would be considered when trying to find models that are both accurate but run efficiently on a CPU. And why exactly CPU? Because CPU is probably the most common processor in the world these days, and you can find it everywhere, and more importantly, it is cost effective. Okay, so in our quest to get accurate and fast model, we need to understand what affects the runtime of a model. So the two main players, of course, the architecture and the target inference hardware, but this is not exactly the complete picture, as you guys know, as part of OpenVINO Dev conference. So two more important pieces in the puzzle are modern compression layer, which include quantization and pruning, and of course, the runtime compiler, such as OpenVINO, the main star of this evening or morning, which help to optimize connection between network and the target hardware. Together, these layers form what we like to call the inference stack. So now we'll go layer by layer and see and analyze its effect on the runtime of the model. So we'll begin with the bottom layer of the stack, which is the hardware. So unfortunately, most of the time, the hardware is not a moving part, but it is determined beforehand by application and business constraints. And runtime is, of course, highly dependent on the hardware, but however, models may perform differently on different hardwares. So since this is a CPU fest, all of our examples are given by CPU. So say like in the OpenVINO. So our first example is two detection models, famous detection models, the YOLO V5 and the SSD MobileNet V1. What we see here is two benchmarking results, one on Intel Core i7, one on Intel Core i5. This is a throughput, so faster is higher, higher is faster. And what we see is that the SSD MobileNet is slower on the Intel Core i7, while it is faster on Intel Core i5. Okay, so it's not exactly predictable to know if ranking among networks will stay after on a different hardware. And another interesting example that illustrates this point comes from an iClear paper, iClear 2021, called Howard NAS Bench by Lee et al. In this paper, they compared the correlation between the runtimes on different hardwares. Each square is the correlation between the average runtime on different model benchmark on a certain hardware. The correlation on the diagonal is 1 because it is the correlation between the same hardware. So for instance, we have here the correlation between runtime performance on a Raspberry Pi 4 and the Google Edge TPU So the correlation between them is only 0.31. Okay, this is basically, it means that if you run your measurements on a Raspberry Pi, don't expect to get the same behavior on an Edge TPU. Okay, so maybe a very useful tip that we always use, and I assume most of you know it, that in case the inference hardware is already known in the beginning of the project, then you should definitely measure the runtime of your candidate architecture before you begin with the training. Okay, this is an important step and will save you precious training time and cost. And in most cases, the runtime of a model wouldn't change after training, at least not dramatically. So we talked about hardware and how it affects the model selection process. We move to the other part of the inference stack, compilation and quantization. Pruning is left aside in this talk. And so these models can improve runtime and reduce memory footprints and model size, but they don't always work in a predictable manner across all models. So let's take a look on this example. So one would think that compressing a model by a factor of half would make it twice more efficient, which this is almost correct if you look on the model size. So over here, again, this example is, as all of our examples is on CPU. I think here it's a Cascade Lake. And we have here runtime of models compiled with OpenVINO on different quantization levels. And we see the model size is indeed cut by a major factor within every quantization. But on the other hand, if we look on the runtime, like latency of the model, you will see that it barely changed within quantization to FP16 and even to int8. So it's a major quantization, but it stays the same. And again, as in the previous example from the hardware choice, we see that quantization doesn't really affect all models equivalently. It might change rankings between model runtime. So, for instance, over here we have two models again on OpenVINO Cascade Lake with 16 visual CPUs. Here it's latency, not throughput, so lower is faster. So we have here ResNet 18 is slower from Efficiency B0 on FP32, but when we quantize it to int8, we see a major improvement in ResNet 18 and not so much improvement in Efficiency B0, and actually the ranking is changing. ResNet now is faster than Efficiency. Okay, so not all quantization doesn't affect uniformly all of the networks. And putting all of it together, there are so many factors and parameters you need to take in consideration that have dramatic impact on the inference performance. Each layer of the stack has different needs, and it's pulling to a different direction. You want to cover most ground and get the best performance, but how exactly? So I think that in DESI, we believe the solution is you must probe the entire inference stack. Okay, so while you develop your model, okay, while model selection, you have to be aware of all of your inference stack, the compilation, the quantization, the hardware. And this can be done manually. So for instance, MobileNet was developed, not MobileNet, but many models were developed manually for a specific hardware. For instance, the new rep VGG was not so new, a year ago. This was developed for a GPU. So people checked what is good for GPU and develop a network that runs fast on a GPU. But you need to be, it's not exactly a science, it's more of an art to understand, to find good networks for all of these moving parts. And this is where we believe neural architecture search come into play. So neural architecture search is a class of algorithms that automatically generate neural network under specific constraints of budget, latency, accuracy, etc. The common NAS, which is short for neural architecture search, approach. So the common NAS approach uses reinforcement learning and build around a controller that each step decide the optimal changes in a given architecture. So for instance, MobileNet and Efficientnet were found in a similar approach. The problem is this process is very expensive. Okay, so in order to understand how each change affects the model, we need to do a lot of training, takes a lot of time, takes a lot of cost, and it's not a surprise that MobileNet and Efficientnet were done by big companies like Google. So how does DESI support production-aware NAS? The DESI solution takes as input a baseline model, the data, the inference environments, and optimize the architectures of any deep learning model to ensure it meets the inference requirements and work well in production. So more formally speaking, our AutoNAC, which is the engine of our NAS, attempts to solve the problem of maximizing objectives such as throughput or minimizing latency, given a customer baseline accuracy. We frame this problem as a constraint optimization problem with multi-objective loss, fully aware of the entire inference stack. The biggest challenge and the biggest time consumer, resource consumer is the model training. Okay, so which can take up to weeks for even a single model. We can generate a search space containing millions of architecture, but we need to be able to know which one will be at least as accurate as the model we want to beat. So our search strategy success lies in our ability to estimate the accuracy of a model after training without fully training it. Okay, so this actually ideas is what brings DESI to this game. We don't have the same resources a huge company like Google, Tesla, Amazon have. So we need to think of smarter, faster ideas. And this may be what we call our special sauce, secret sauce. AutoNAC is 100 times faster than the common NAS algorithm. It roughly runs around 3 to 4 times slower than a training time of a single model. Additionally, it allows optimization of any performance objective, and it is applicable to a wide range of domains and tasks. So after we introduced our AutoNAC engine, now we can talk about some results of this system. We'll start with results of the classic Imagenet classification test. Over here, we see a graph of latency versus accuracy on models compiled quantized with OpenVINO on a Cascade Lake CPU. Over here, this is the baseline, all the classic families of networks, MobileNet, ResNet, RegNet, RevVGG, Efficientnet. Also, we have here the new version of ResNet 50 by Ross Whiteman, which got a nice boost to the classic ResNet 50. As we mentioned before, what we are searching for is networks which are both accurate and fast. So basically, we want to be as left as we can and as above, like the rest of the networks. Basically, there is no perfect spot to be in. It's not, for instance, not clear if efficient B0 is better than efficient B3 because it's faster, but it's less accurate. So we usually like to predict a family of networks. So the AutoNAC doesn't output a single network; it outputs a family of networks, which lies on the hopefully on the good trade-off locations of accuracy and latency. So this is our results of our engine. As you can see, our models lies above and to the left of the rest of the model, and we get impressive boost in performance. For instance, efficient at B3, we get boost of 2.42x times faster than in our model, and a slight improvement even in accuracy. Also we can see in resonance strikes back almost twice faster with same accuracy, and efficient at B1 3.14 times faster, which is very impressive performance. And to again highlight these results, we also submitted some of these models to MLPerf, which is a competition of runtime performance of different deep learning tasks run by Intel. And what we submitted these models into what's called the offline scenario, which is to optimize throughput in the case of image classification. So we see we get basically we tested our models on 3 different CPUs, Intel Ice Lake and Intel Cascade Lake with different cores. We see, for instance, on Intel Ice Lake with 32 cores, we get versus the baseline of Resonant 50 with 32 bits, we get 10.4 times improvement. And if we also give the Resonant 50 an 8-bit quantization, we get still get 2.8 improvement. So basically, this means like OpenVINO can get you to good results with networks, but if you don't change the network architecture, then you are stuck in a ceiling. You have to play with architecture. Like compilation is not enough. Another interesting results you can see here is how we improved from a year ago. It's 2020, but it's a year and a half ago. And we tried to compare results of DESI, and we didn't do it with the same machines exactly, so we divided by the number of cores. So we see that DESI together with OpenVINO, we managed to get twice, we managed to get 187 image per core versus 137 for Nesty, which is 36.97 improvement. And we believe a lot of it is because we improved our NAS, and a lot of it also because OpenVINO improved their compilation. Another interesting results of our NAS is in NLP. Again, our NAS is task oblivious. We can feed every task we want to solve. We basically can solve it. It doesn't has some unique task it can work on. Basically, if you define the task, the hardware, the data, and all automatically fits into it. So in order to prove this, we went to a new field we weren't expert in it before. So this is the NLP, the task of Squad V1, which is a question answering task. And we try to improve the performance of the famous BERT architecture. Over here, we see the results of AutoNAC produced DESI models. We had one called DESINet BERT large 2 and one DESINet BERT large 1 and DESINet BERT large 2. As you can see, the F1 score on Squad V1 of BERT is 90.6. So we have DESI-BERT large 1 is a bit less accurate than the BERT, but it is much faster. And DESI-BERT large 2 is a bit more accurate, but it is faster, but a bit slower. This is this bluish, the darker blue is the DESI-BERT large 2. If we talk about numbers, we see that over here we have DESI-BERT large 1. So this is the less accurate but faster one. We get improvement of 10 times faster than the 32-bit BERT large. And versus the 8-bit, we get 4.6 times faster. This is on Intel Ice Lake 32 cores, and same trends on 16 cores. And on the other model, the DESI-BERT large 2, which is more accurate but less, not as fast as the DESI-BERT large 1, we get still an impressive performance boost and 7.7 faster in 32 cores, and then the baseline of 32 bits, and 2.46 faster in the 8-bit. Okay, so we have many more results. You can check a lot of them in our website if you want. We just highlighted a few of them that are really regards to OpenVINO. Again, OpenVINO gave amazing boost to these models on CPU, but I think the main idea is we want you to take is you need to be aware that you will be using in the end the models with OpenVINO while you choose your model, and then you might get even better performance with OpenVINO. And to end this talk, we'll give you a few tips about maximizing CPU utilization. One tip is, the first tip is to basically, in case you do have an option to choose from, for instance, if you use AWS machines, is to find the optimal number of cores that will be used to inference. So as you can see here, we get the latency of BERT base versus number of cores, of CPU cores. So you see on one core, we get on 2 cores, we get better results than on 1 core, and on 4 cores, we get better. But it's not a linear improvement, it's more of a log. So we get in the end a diminishing returns. So you need to find like the sweet spot of cost runtime trade-off in order to maximize your cost and the runtime. And also you need to take in your mind that model size and structure heavily affect memory bottlenecks. So you don't see the same trends in every network. So for instance, in mobile BERT, and you get much more diminishing returns. It's faster than in DESI-BERT. So you get different sweet spots for every network. And our second last tip is if you want to optimize throughput instead of latency, then what we really suggest is, highly suggest, is to optimize throughput by running in parallel. So you have a model basically what we mean is instead of, for instance, using 8 core, one model on 8 core, replicate a model, 2 models, 4 core each. In this case, you can get much better results with parallelism, and you get better CPU utilization. This is tip is combined again with the previous tip of finding the sweet spot. So another sweet spot here is the number of replicas versus how many cores, and you have interesting trade-offs. If you like to talk about it more, then you can ping us on our website. We have a good automatic solution to these scenarios. And that's it. If the one thing that I'd like you to take with me from this session today is the importance of taking account production constraints while you select your network. Hardware awareness earlier in the model development stage is critical for model selection and performance optimization. Common optimization practices are important, but are not enough. And there is a limit in terms of boost that you can be achieved with quantization, compilation, and pruning. And we see that if we take all of this together, all of these constraints while we select the model, we get impressive results, both in different worlds, such as NLP and computer vision. And that's it. I hope you enjoyed my talk, and if you have any questions, Shai will be here to answer it, but you can also send us by mail. Thank you very much.
Hi, everyone. Thank you so much. Amos, that was great. I learned a lot. This is truly the better together story, right, Shay?
Yeah. So I'm going to address now the some questions I got. So first off, I was asked, if I need more models to run than available cores, how it affect latency? So something that we and other research groups have found that essentially cores as some capacity, some limits. That's why it's important to fit the models that runs on the specific hardware, whether it's one model, whether it's an entire stack of models. So running parallel models on a single CPU might cause degradation in latency, obviously, but if you take all the models into account when building them, then it would greatly improve latency and throughput and so on, mostly due to efficient memory allocation using smaller models. But essentially, that has an high impact.
That's great. So one other question is, can you describe the process of operating your NAS?
Sure. So our NAS algorithm, for example, for CPU based hardwares, is essentially an automated process. We have a platform online where people can log in and upload their model. Even if they don't have one, they can simply download one from our available model zoo. And then the optimization starts by essentially spanning a large candidate search space from which the optimized models will be selected and then be available on our platform to download and train, fine-tune, essentially play with them for as much as you like. And following that, again, we can repeat the process with several models with several KPIs, whether it's throughput, memory, latency, and so on, and for several tasks as well, whether it's object detection, segmentation, classification, and so on. I see that we have another question. Any certification program? So again, we have several products supporting the deep learning development pipeline. From training using our open source supergradients package and our platform, which I described earlier. So all of those can be publicly accessed, and all of them have, the platform has a pro user program and to get that, you need to contact us via the platform, but there is some level of abilities that are free, and you can try them out right after this session.
Great. Is there anything else you want to add, Shay? Like how do people get started, or how can someone use your NAS?
So usually we meet developers at different stages of the development process, whether it's at the initial stages where they want to select the best CPU for their application, or at early or later stages, when they have a system up and running in their lab on a strong machine, and they want to deploy it or reduce cloud cost on some CPU server or CPU edge device. We usually deal with all scope of the development process. So if they in the early stage, they can use our pre-optimized model from our model zoo. If they already have a model they would like to simply shrink, we can help them with that process. But again, everything is available within our platform. You can simply log on, evaluate, upload your model, and then get the optimized model in exchange.
Awesome. That was great. I learned a lot. Really appreciate your time. Thank you, Amos and Shay, and everyone here who joined us at DevCon. Have a good rest of your conference. Thanks, everyone. Bye.
Thank you, everyone.